Hi, this video is aimed to introduce our latest work in IPSN 2021, MagicInput, training-free multilingual finger input system using data augmentation based on MNISTs. Traditional text input system has certain limitations in some scenarios. Touchscreen input systems become inconvenient when users wearing gloves, and suffer from a fat finger input problem on small-sized touchscreen devices, like a smartwatch. Voice recognition systems also have user privacy issues in a public place, and they may not work well in a noisy environment or when users speaking accents. Therefore, researchers are now focusing on a novel solution of the text input, writing in the air. When we deploy the air writing technology on a mobile device, it can improve the user's input experience by expanding the small size of the touchscreen into a bigger 3D space in the air. Currently, there are three main technologies to implement air writing. They are vision-based, radio frequency-based, and acoustic-based methods. The first two types of methods have some limitations. Only that they require specialized equipment, like a camera, or IR sensors, Wi-Fi APs, or FID readers, which may not be available on mobile devices, especially on the smartwatch. Another limitation is that both the image processing and RF frequency signal processing are complicated, which causes not low power consumption. Therefore, we think that the acoustic-based methods are more attractive for two reasons. One is that microphones and speakers are already available on existing mobile devices. The other is that audio data processing has a relatively small amount of calculation, which makes it power-saving. In this study, we tried to use the acoustic-based method to implement a novel air-writing text input system. Here, we will briefly introduce the principle of acoustic-based finger tracking in one-dimension space. The speaker built in the device sends out a continuous wave in inaudible frequency, like 18 to 22 kHz, and this sound wave will be reflected when it meets the finger. The reflected signal is then received by the microphone built in the device. Estimating absolute distance accurately in real time is an open problem because the acoustic channel is not sparse. So, the effective tracking algorithm is to calculate the distance in two parts. One is the initial distance, and the other is the sum of the relative distance changes, which can be calculated based on the phase change of the channel impulse response with high accuracy. Tracking in 2D space can be supported if the mobile device has at least one speaker and two microphones. For each speaker-microphone pair, the abyssal distances from the finger to microphone 1 and microphone 2 need to be calculated. We can obtain the 2D coordinate information, x, y, of the finger, by using the triangulation method. The accuracy of x, y, mainly depends on the estimation accuracy of the two 1D absolute distances, d1 and d2. However, there exist cumulative errors during calculating absolute distances over time. What's worse, according to the formula, the error in the 1D absolute distance will be reflected in the error of the 2D coordinate in the form of a squared term. So we can see that when there is a small error in 1D distance estimation, the coordinate of x, y, will be shifted as a big error. We built the 2D tracking test bed, and then recorded the results of 2D tracking and ground truth at the same time. We found that with the increasing times of writing, the error of 2D tracking is also increasing, and cannot recover the pattern of letters. Therefore, 2D tracking is not suitable for text input systems. Let's back to discuss 1D tracking. We find that when a user writes a letter with his finger, the 1D trajectory pattern is only determined by the relative distance, and the errors of that relative distance only accumulate from the start point to the end point of writing a letter. Therefore, the cumulative error can be cleared to zero at the beginning of writing each new letter. We built the 1D tracking test bed, and let a user write 4 lowercase letters A, B, C, and D for 50 times. We record the corresponding 1D trajectory patterns and show the results here. We found that the 1D trajectory pattern is stable over time and there are obvious differences when writing 4 different letters. By the way, 1D tracking only needs 1 speaker and 1 microphone. So we believe that the 1D tracking technique is more suitable for the text input system. To further verify the feasibility of classifying letters with 1D trajectories, we collect the datasets of 26 lowercase English letters for each of 3 different users. We first use dataset 1 to train a random forest classifier and test it with user 1's data. The performance of the classifier is good. We try to recognize user 2's data with the same random forest classifier. We find that the results are very poor, which shows that the different writing habits have a great impact on the performance of the classifier. We retrained the RF model using the 3 users' dataset together and tested it with user 2's data again. The result shows that the trained classifier can work well if the dataset is large enough to cover the target user's writing habit. To summarize, 1D trajectories have enough information to distinguish the lowercase letters with high accuracy. And the dataset that includes the target user's writing habits is important. However, during the application scenarios, it is unrealistic to collect a large-scale training dataset or collect personalized dataset for each unseen user. Therefore, we need to adopt some methods to bypass data collection step. A good news is that MNIST datasets are online and can be easy downloaded. MNIST datasets have many advantages, they cover thousands of volunteers, and they have many versions of languages. These MNIST datasets provide us an opportunity to generate a large-scale 1D trajectory dataset. So, how to convert the MNIST images into the 1D trajectories? In this study, we solved this problem in 2 steps. First, we restore the stroke order information on each image. Then, we simulate the distance changes in 1D space between the finger and the mobile device. We first introduce the algorithm of restoring the stroke order information. We compared 3 datasets. We download instructional videos for handwriting from the internet. By analyzing each frame of the video, we can obtain the reference information of the standard stroke order and the writing direction in each timestamp. Then we input a handwritten image and find out its key points by determining whether the degree of a point is odd. We select these key points as starting points in turn. After that, we initialize a particle swarm on the starting point, which are given directions according to the reference information of the corresponding timestamp. Each particle moves forward with its own direction, and the particle will be eliminated in the next timestamp if it moves outside the border. The above steps are repeated until the final moment. In the last, we record the trajectories of the living particles so that we can restore stroke order information for the image. We also found that different users will have different writing habits when writing the same letters. Take the letter F as an example. We show the instructional video of writing a print F. In the MNIST dataset, there are mainly 2 styles of images of F. One is to write F in the common style like a print F, and the other one is to write F in a continuous stroke style. For the images that writing F in the common style, we follow the reference information in the instructional video of standard F. Then we can recover the stroke order information through the particle swarm-based algorithm. For the continuous stroke style, we manually add the parts of the continuous stroke to regenerate the reference information. Similarly, we use the same particle swarm-based algorithm to recover the stroke order information. Up to this step, we can convert the MNIST image into a GIF. Next, we try to convert the GIF into the 1D trajectory. We build a 3D coordinate system with a simulated phone as its origin. Then we calculate the distance from the origin to each point in the GIF. And finally, we can generate a 1D trajectory pattern. When the user writes the letters with multiple strokes in the air, the user's finger jumps from the ending point of the previous stroke to the starting point of the next stroke. This jumping motion is also recorded by the 1D tracking system, so we need to simulate this jumping motion during data augmentation as well. In our paper, we used the second-order Bessel curve function for the finger jumping simulation. Until now, we have completed the conversion from an MNIST image to a 1D trajectory. Our algorithm can also support the MNIST datasets of other languages. Here we take Chinese as an example. We obtain instructional videos of writing a Chinese character and use the algorithm to convert the images into a GIF. This GIF contains detailed information about the stroke order sequences when the volunteer wrote this Chinese character. Then we can simulate the final 1D trajectory pattern, as shown in the right picture. Now, we present the entire pipeline of our proposed MagicInput. First, acoustic-based technology is used to record the 1D trajectory of the user's finger motion, and we use a letter segmentation module to obtain each letter's 1D traces. Then, we judge whether the personalized dataset has been updated. If not, we go to the warm-up stage. The warm-up stage is to use the general pre-trained classification model to output top K result for the user. The selected results are uploaded to the server. On the server side, we use the user's trajectories as templates, and search the top M most similar traces from the track MNIST. In this way, we can build the personalized dataset that matches the user's writing habits. Finally, we download the personalized dataset on the mobile device, and utilize the KNN classifier to output top 1 classification results with high accuracy. In the evaluation section, we verify whether the artificial dataset can match the target user's writing habit and help to improve classification performance. We compared 3 datasets as shown on the left. The first one is the artificial dataset generated from track MNIST that matches the user A's writing habits. The second one is the dataset collected by the user A himself, and the third one is the dataset collected by the other user. We used a KNN classifier to classify user A's testing data. The results show that the artificial dataset can almost achieve the same performance as the user's collected dataset on his own. We have conducted rich experiments to verify the feasibility and robustness of our system, and the audience can read our paper to get more detailed information on your interested evaluation results. In conclusion, we designed a novel text input system called MagicInput that enables air writing on mobile devices. We proposed a novel data augmentation for 1D trajectories based on MNIST datasets, which supports multiple languages and covers various writing habit simulation. We also proposed an online matching mechanism to build a personalized dataset that implements a training-free manner. The above all is our video, and thanks for watching.